All right, so now let's do the momentum conservation equation. From your first year physics class, maybe you know of momentum conservation as Newton's third law, action equals reaction. And you could think of this as if, for example, two masses collide, they will change their velocity. So the momentum of one particle is transferred to the other one. And so if this one gets a plus momentum, this one gets the equal and opposite momentum going in the other direction. In other words, you took momentum out of the first mass and you put it into the other one. And so it's a conservation of momentum, that Newton's third law. Right now we're going to use that conservation principle, we're going to apply it to a fluid, a continuum. So we're going to start off with writing Newton's second law, F equals ma, and we're going to do this for, in a Lagrangian point of view, for a mass particle. And the reason we do for a Lagrangian particle is that F equals ma, Newton's second law, applies to a fixed amount of mass, certain material, right? When you calculate the forces on a ball, for example, a baseball, you calculate the force on the ball, not on a fixed volume of space, but on the ball itself, and you integrate the forces and calculate the acceleration, always on the same ball, right? So that's a little bit different than the Eulerian point of view, where you do a momentum budget for a fixed volume of the ocean, for example, and you calculate the flux of momentum in and out of the fixed volume. All right, so we're going to start off with F equals ma. We're going to write it in Lagrangian form, and then we're going to convert that into the Eulerian framework. All right, so if I'm thinking of a bit of mass in the ocean, delta M, right? That bit of mass can be written as rho delta V, and rho is the density delta V. And the important thing to remember when we're doing the Lagrangian budget is that this delta M is a fixed amount of mass. It's going to move through the fluid, it may accelerate and so on, but it's always the same volume. And in particular, as the fluid gets deformed, it's possible that the delta V will change and that the rho will change, but the rho times delta V will not change. We define delta V to enclose all the mass we had at the beginning. Okay, that's the delta M, and then there's going to be forces on this, and we're going to pick forces F to be per unit volume. So the force will be the force per unit volume times the volume, and that will be the force. Right, so F is per unit volume. Now, if we write the Lagrangian F equals ma, so we have d by dt of the momentum, delta M times the velocity of that mass, is equal to the forces, F times delta V. So this is just Newton's second law. F equals ma, or d by dt of the momentum, mass times acceleration. Okay, now we remember that this delta M here is a fixed amount of mass, so it doesn't change with time, so we could pull it out of the time derivative. So we end up with delta M d by dt of the velocity is equal to F times delta V. This now is starting to look like F equals ma, except we wrote F here as F times delta V because F is per unit volume. If I divide both sides by delta V, then I'll get delta M divided by delta V, that's just the density, rho dV dt is equal to F. And this last equation, red marker, this last equation is conservation of momentum equation for a Lagrangian particle. So this is momentum conservation in a Lagrangian framework. In other words, following the material as it moves with velocity v. All right, now we want to convert this into an Eulerian framework. So the Eulerian one, where we have a fixed volume and we do a momentum budget, is much easier to work with in numerical models and to think about. And the reason is, if you imagine following the material, if the fluid is turbulent, if you have a little box of fluid, over time that will get sheared out and stretched and mixed up, and it will be a big spaghetti diagram of following every particle in a fixed volume if we try to follow the mass. And it becomes very unwieldy very quickly to do a calculation in the Lagrangian framework. So what we want to do is we want to do a momentum budget, but for a fixed volume in space. So to do that conversion into Eulerian, we use the material derivative that you worked with in the homework. Remember, the material derivative, d by dt, is equal to partial t, or is defined, plus v dotted with gradient, right? Where v is the velocity of the material. And so if we apply that, definitely this v is the velocity of the material, is the same v we have over here. So I'm going to apply d by dt of v. I'm going to substitute in here this expression. So I get rho dv dt plus v dotted with gradient of v is equal to the F, force per unit volume. And this is the momentum equation from an Eulerian point of view. Momentum conservation Eulerian point of view, a framework. All right, we want to manipulate this one more time. So I called it the momentum conservation, but it's not clear that this is a conservation equation. It doesn't have the usual form of partial t of a quantity per unit volume is plus the divergence of the flux of, or the divergence of the current of that quantity is equal to 0. And so we want to rewrite it in that form, that usual conservation law form. And we're going to do it. To do it, we're going to bring, right, we have partial t of the quantity of interest. In this case, it's the momentum per unit volume. So momentum per unit volume is just rho times v. So I want to bring the rho back inside this partial derivative. And in so doing, I will have to subtract out the v times partial rho. And massage this into the right form. So let me do this. And you'll see along the way that I have to use the mass continuity equation that we derived in the previous video. Okay, so if I want to get it in the conservation form, I'll do d by dt of, or rho d by dt of v is equal to d by dt of rho v. I brought the rho inside the derivative, so I have to subtract out minus v d rho dt, right? Because if I expand this out using the chain rule, the product rule, I mean, I'll get this term plus this term, a term like this, so I subtract it out. All right, so then I could substitute this expression instead of that, or instead of this term. So what I'm left with is d by dt of rho v minus v partial t plus rho v, rho times v, dotted with gradient of v is equal to f. Okay, and now this term here, I'm going to use the mass continuity equation to eliminate d rho dt. So remember, d rho dt plus div dot rho v is equal to 0. This is the mass continuity equation, right? It's the conservation form. The mass per unit volume, the partial derivative of the quantity, plus the divergence of the current of mass, which is just rho v. And so we're going to, that means partial rho partial t is just minus div dot rho v. And so partial t here, I can replace it with the negative of this quantity here. So what I get is, just decide here, this is mass continuity. What I get is partial t of the momentum per unit volume minus v, and then d rho dt is, right, d rho dt is equal to minus div dot v. And so if I replace d rho dt by that, the minus will become a plus, and then I have div dot rho v. That takes care of this term, plus rho v dotted with gradient of v equals f. All right, so it's looking good. Now we're almost at the right place where we want it. So if you look at this bit here, I have the v times the derivative of rho v plus rho v times the derivative of v. That's just like the product rule, right? And so these two terms here, they combine into divergence of rho v v. And so then my equation becomes partial t rho v plus div dot rho v is equal to f. And this now is in a proper conservation form. So this is the quantity q here is rho v, which is the momentum, or q is the momentum per unit volume, and that is just equal to rho v. And the current of momentum, and I'll write as a big bold matrix here, is rho v v. And this is the current, the momentum. Current, or the momentum per unit volume current, momentum density, or momentum per unit volume. Call it density. Momentum density current. And it has this strange VV here, and that means that it's a matrix. It's a tensor or a matrix. It's got 9 components. It's a 3 by 3 business. And that's because momentum is a vector, and then the current is a vector. So you have the vector of a vector, or the transport. So you pick a direction, and then you transport a vector along that direction. And so the direction in which you're transporting stuff needs 3 components, and then the quantity you're transporting is a vector with these another 3 component. 3 times 3 is 9. And so this here is the momentum current tensor. And this gives us our equation. So if I write it up here, I get the following here. I'll write it one last time. D by dt of rho v plus divergence of rho v equals the forces. And I've left a little bit of space over here because some of the force that we put in F can equally be put in here. So whether we put them inside or put in on the outside is totally subjective. There's no objective way to decide. But one force in particular that we might want to put inside is the pressure force, right? The pressure force is a stress, is a normal stress, the force perpendicular to the surface. And that particular force, which is gradient P, can be rewritten and put inside this term. And sometimes people do that. And so I want to put it that way. So if I do that, the pressure force, right, F P is equal to minus grad P. And we can write that, right, this is the same thing in Cartesian. That's equal to dp dx, or minus dp dx, minus dp dy, and minus dp dz. And it could also be written as the divergence of P 0, 0, 0, 0, 0, 0. Right? And the reason is if I take the divergence of the first row, what I get is dp dx plus 0 d0 dy plus d0 dz. I just get a dp dx. So the divergence of the first row gives you, oh, I need a minus here, minus. The divergence minus the divergence of the first row will just give me dp dx. Minus the divergence of the second row will just give me minus dp dy. And minus the divergence of the third row will give me dp dz. And so we can see that this business here is the same thing as minus div dot p times the identity matrix, or the identity tensor. And now I can bring this quantity over on this side and include the pi inside the current vector for momentum density. And so this now becomes plus P times the site energy. And so this business here is this big J here, including the pressure tensor. And this is the remaining forces. So for example, e.g. force of gravity, and maybe some other forces that we may have in the fluid. Okay, so this is the momentum conservation, right? We have if there's no forces, momentum is conserved, and this equation just says that this quantity here is the movement of momentum around in space, and the only way that the momentum density will change is if there's a divergence or convergence of this momentum current. So if momentum is bunching up in some place, the momentum will go up, and if it's spreading out, the momentum will drop. But it's in the right form for conservation equation. All right, so the next step will be to revisit these equations in the context of energy.